Godel Universe is something which is very near to my heart. First time I came across its mention was in Roger Penrose's book, The Emperor's New Mind. And Godel is famous for something else altogether. Godel was a logician, and he is known for his incompleteness theorem. What that states is that in any given system of axioms, there will be certain truths which you can prove they are true, but there will also be certain truths which are not provable within that system. Similarly, there are certain falsehoods which you can prove they are false. On the other hand, there will be falsehoods which you cannot prove that they are false. So he said that any logical system, it had a certain incompleteness, and that is called his Godel's incompleteness theorem. The first theorem was actually on the set of natural integers, and it described that certain statements about the integers could not be proved to be true or false. That's his logician aspect of his personality. Now Godel and Einstein, they left Germany and they came to Institute of Advanced Studies at Princeton, and they became very good friends over there. And Godel was inspired to do study and research on general relativity by Einstein himself. Now the great thing about the two is they never learned to drive the car, and they used to drive the considerable distance from the home to the institute. They used to take walks. Einstein's house was closer and Godel's house was a bit farther, so Godel used to walk to Einstein's house, and both then used to walk together to the institute and then back again, discussing maths, physics and philosophy. So Godel made a remarkable birthday present to Einstein, his 70th birthday present. In 1949, he found a new cosmological solution to Einstein's equations, which had the same matter distribution as the Einstein universe, and he presented this to Einstein as a birthday present on his 70th birthday. Now, there is this beautiful movie by the title IQ, and to my pleasant surprise, not only it showed Godel and Einstein, it also showed Podolsky and Rosen, the people who were part of the formulation of the EPR paradox, which is well known. And yes, so I was so sort of, you can say, thrilled that here's a movie Einstein, Podolsky and Rosen, who are not such a well-known character set, but the EPR paradox is famous. It's been almost 80 years and it is still relevant today. That these two characters, Podolsky and Rosen, are portrayed in this movie.
What does IQ stand for?
IQ is the name of the movie.
I know, but what is it short? Is it short for just the IQ test, the IQ?
Yeah, intelligence quotient is short for that. This is the main question which arises. Does the matter determine geometry of the universe uniquely? That was Einstein's initial motivation and vision, that his field equations should determine the geometry of the universe uniquely. But the Godel universe, it was a counterexample, because it had the same matter distribution as the Einstein universe, but it had other number of different paradoxical properties. So the cosmological constant had the opposite sign. The universe was rotating. The past and future were accessible, and path of light rays and other particles were helical. Here I want to show you the light cones in Godel universe. But before that, I'll quickly summarize for you the light cone of Minkowski space, the simplest light cone. This blue surface represents the present, and in this cone, the time-like direction, this region is called time-like. This region outside the cone is called space-like, and the region along the cone, that is called light-like, also the null direction. So what happens in Godel universe is, as you go away from the rotation axis, the light cones, they start opening, they start becoming wider, the angle increases of the cones, and they start tilting. Now this doesn't happen in Minkowski universe where the light cone is same everywhere, but here the rotation affects the structure of propagation of lights in such a way that the light cones, they start opening and tilting in the direction of rotation, and as a result there arises a situation so that travel to past and close time like curves, they become possible.
So what maintains constant during this process?
The constant rotation.
No, I mean the cone at the center is it's narrow, and it become wider. That's because certain things is a constant. Is some kind of flux or something that guided, like to be like. So what determines that?
Actually, you see, light cone depends upon the velocity with which you are moving, and the rotation of the universe, it couples to the propagation of light in such a manner that the what happens is, you can see if this is the position of the light cone, that means light ray is traveling in this direction, and over here light ray is traveling in that direction. So this is because the light ray has got coupled to the rotation of the universe. Over here the rays are not coupled to the rotation, they are at the center. But as it gets coupled to the rotation, it starts tilting. The path of the light ray starts changing.
Okay, but yeah, it still didn't explain the angle. Like why it opens up certain angle. Right?
There's a relationship which describes how much the angle opens up. And basically it comes from the geometry of null rays. We write dA square as a line element, and it is written in terms of the metric tensor G mu nu dx mu dx nu. These are the space and time coordinates. Nu goes from 0 to 1, 2, 3. So the metric tensor of the Godel universe, it is not diagonal. For example, the Minkowski metric tensor is just -1, -1, -1, and all this is 0. But the Godel metric tensor, it has off diagonal terms. It has a term over here, you can call it as GT phi. Phi is the direction of rotation. Let me use, this is T, this is R, and this is phi for rotation, and this is Z. Z is the direction of axis along which the rotation takes place, and phi is the angular parameter which describes the rotation, and R is the radial distance from the origin.
So Z is the direction of the rotation, but this Z direction, is the Z direction always constant?
Yes, that is a fixed direction in space. That's why the Godel universe is called anisotropic, that all the directions are not the same. There is a special preferred direction in the universe. So we have two off diagonal terms, GT phi and G, magnitudes the same, and then here rest of it is there are some terms here GRR and G phi t. So when we write down this equation, ds square is equal to 0, that determines the direction of the light rays, because ds square is equal to 0 for the light rays. That gives us a formula, and from that formula we get the angle of tipping of the light cone and opening of the light cone. Yes, so here we have a more comprehensive picture of what is happening to the light. So light rays, they start from the origin and they start spiraling outwards. They don't go radially outwards straight away, they start spiraling. They reach a point of maximal expansion and then they start spiraling back in again, and finally they reach back to the point of their origin. So light rays are not going to infinity, they are coming back to the starting point. And the point of maximal distance, it's called the horizon of the Godel universe.
Seems the Godel universe is talking about just like kind of like a one galaxy.
No, it applies to the whole universe. It is what is called as a dust solution, but the dust particles in the cosmological scale, they represent each galaxy, like each galaxy is taken as a particle of dust. So it is a pressureless solution in the sense that the gravitational force of attraction or repulsion is very weak, they are very far away from each other. So it's considered as a pressureless dust, and the speed of rotation of the galaxy is considered as the rotation of the dust particles or the vorticity of the dust particles.
So it seems clear, seems locally there is kind of like a rotation axis if you look at the solar system, the galaxy, right?
Right.
So it's anisotropic.
Well, yeah, but so I'm wondering, I was trying to Google right now Fang's question. So when Einstein was 70, it was the year, when did we discover that there were galaxies other than the Milky Way? Does anybody know that? It wasn't very far apart. In other words, when Gödel thought of this, it was either a short number of years before or after astronomers discovered that there's more than one galaxy in the universe. This is relatively recent. Like when Einstein wrote the special theory of relativity, it was not known that there was multiple galaxies. So I wonder if Gödel thought of this under the regime of one galaxy or under the new regime of many galaxies.
Yes, I can answer that question. In Godel, in his own paper, this first 1949 paper, towards the end he considers a system of galaxies, and he considers the speed of rotation of galaxies and compares it with the angular velocity of the universe, whether the angular velocity of the universe is related to the angular velocities of the galaxies. And he does says that his model requires a expansion to be built in to expand the explain the redshift of the distant galaxies. So he was aware of the expansion as well as other galaxies.
So I think that this is a remarkable insight that seems logical, because a lot of cosmologists and quantum gravity theorists are recognizing that a proper quantum gravity theory behaves as a superfluid. Space-time, that is, behaves as a superfluid. And the thing about rotation is there is no object in the universe there is no asteroid not rotating. There is no planet that is not rotating. Everything is rotating. And so when you think about a superfluidic space-time from the Big Bang at some radius, let's say some radius from the Big Bang was only 100 meters, and now it's much larger. But you have only two choices. Either it's rotating or it's not rotating. And if it is rotating, it's distinctly helical, meaning they could have rotated the opposite way, or it could have rotated on a different axis, but it's not. It's rotating on that axis.
Yeah, it has an axis. It's not spherical rotations
Right.
that we talked about.
Oh, right.
Yeah.
Spherical rotation.
Meaning
Oh, right. Oh, yes.
Your
yes.
the axis is
Right.
rotating. So yeah.
Oh, well, Moni, is it possible that the axis can rotate? Does Godel's universe require a fixed, rigid axis? Because a fixed, rigid axis does not seem physically realistic.
He said yes. I just asked him the question.
Fixed. So why is it fixed and rigid if that's what your answer was?
Actually, the situation is slightly
And how can it be? How can it be anything? How can it be? It's relativistic. In other words, if it's the universe, that's everything. Therefore, you can't have an alternating axis. It's an illogical statement.
Locally, every system locally, the axis seems to be fixed.
Locally.
Yeah.
the direction.
Right, but there can't be an act.
Right, but if you look at it locally, I'm spinning my pen, it is fixed. The axis
It's
is
fixed
fixed.
relative to the room. Meaning, what I'm saying is, when you have everything, the universe, you can have no statement about.
Yeah, that's what I'm saying.
rotate.
Locally, only if you look at this local system, it seems to be fixed. But I don't know if the whole universe, like just consider if the whole universe has one axis.
That's what the Godel universe is, a universal axis.
The axis is unique, and the direction of the axis is also unique, and it is same at all points of the universe. So there is a certain homogeneity in the universe, that in the sense that direction at each point is same. So these models are called anisotropic. Isotropic means all the directions is same, but anisotropic means there is a special direction, which is the direction of rotation.
So you mean the whole universe has an axis this way, and then our galaxy has an axis also that way, and the solar system is also that way. Everything is rotating along the axis in this direction.
Well, Godel was addressing this problem, and he said, while there is certain tendency for alignment, and there are certain experimental evidences for a preferred direction, there's a slide later on in the presentation which discusses the experimental aspects of a preferred direction in the universe.
Right helicity.
In the sense of polarization of the photons from radio galaxies. But this axis is unique. I mean, this direction is unique, and it is same for all the points. But the rotation which we find in the physical universe, it's not a perfect alignment. Some galaxies, their axis will be this way. Other galaxies, the axis will be this way. So maybe the original distribution was uniform, but over a period of time, due to various types of perturbations, the axes have got misaligned, but still there is an overall statistical tendency for a specific direction.
I mean, it's like a magnet, right? Before they magnetize, the spins are not aligned. Once it's magnetized, they're aligned. So
Yeah.
I guess this universe is the same thing. They don't have to be aligned in one direction unless a certain field made them
Okay.
align that way, right? Because it costs energy.
Okay. Yes, here just a few definitions. We use the term Godel horizon. This horizon is the maximal distance the light rays can travel from a point before they curve around and start spiraling back in. Now, the interesting property of the Godel horizon is that it is rotating at the speed of light, whereas the horizon of the expanding universe is expanding at the speed of light. So light cannot cross it, or other particles cannot cross it. But in the Godel horizon, the horizon is rotating at the speed of light. So that makes sense, because as we go farther from the rotation axis, the speed is increasing. So that's the Godel horizon. the envelope of these points is called a closed null curve. The null word comes in the context of the light rays, because for light rays the line element is 0, so that is interpreted as null.
Moni. So when Gödel wrote this, the cosmological experimental data for building up to the conjecture of dark energy and dark matter was not available. And part of that conjecture is the rotational velocity. And so you're speaking of that here in this bullet point. Can you relate that? Because now we have new evidence that Gödel did not have access to.
Right. So the rotational curve of the galaxies, when we consider the rotation of a galaxy, we get, aside from the basic redshift from the galaxy, we have a variation in the redshift as we go to points which are distributed at a largest distance from the center. This is because the angular velocity of the stars of those points, it adds up to the angular velocity of the galaxy. So certain stars are moving towards you, so their light is redshifted in a different manner. The points which are moving away from you, their light gets redshifted in a different manner. So we get a distribution of the redshift, which tells us what is the velocity distribution in the galaxy. So the velocities which come out from this redshift data, detailed study of the redshift data of a galaxy, that suggests that the gravitational field of the galaxy is such a manner that it is attracting the stars which are farther away at a rate which is greater than what is predicted by the Newtonian gravity. So that they explain in terms of extra hidden matter, which is called as dark matter.
Isn't it, don't you mean that it's also moving in a way that is contrary to general relativity? Because general relativity does not predict dark matter and dark energy, which is the big problem.
Yeah, that's right. It does not. So the particles for dark matter, they are called WIMPs, weakly interacting massive particles. There are various other candidates also for the dark matter. And then we have another phrase called dark energy, which is related to the expansion, and I'll discuss that in one of the slides. Okay, so two more terms here. One is a closed null curve, and the third is closed time-like curve, referred to as CTCs, and closed null curves as CNCs. So this picture explains how the time travel becomes possible due to the tilting and opening of the light cones. The light cones you see here, they are opening, which you've seen in the earlier picture. But as you go at a critical distance farther from the Gödel horizon, it is possible to cross a Gödel horizon through acceleration, which is not possible in case of the expanding universe. And while staying within the light cone, which means while staying with a velocity which is lower than that of light, you can make a circuit so that you can reach back to past and reach back to the starting point of the values. So it was found that CTCs are not geodesic. That means you require force and energy and acceleration for particles to traverse or navigate the CTC. And calculations were done about that, and very high figures were found for the energy. But theoretically, it was possible to travel back into past.
So Moni, the opening of the cone, what does that say? It's like if the cones open up more, is
Yeah.
there more space like? Or less time?
Yes, if you talk in terms of the volume of the time-like area of the cone, that increases, and the volume of the space.
That's for the closed cone, right?
Yeah.
That's more time-like
Yeah.
than space-like.
Yeah.
Okay. So it's like as though when the cone opens up, it slows down.
No, the light doesn't slow down. Only the directions they change. There's something called frame dragging in black holes also. Frame dragging. Close to a black hole, in the rotating curve black hole, the rotation actually drags the space along with it. So that means you cannot have an object which is stationary at that point. The space itself is being dragged around. So that's called ergosphere for the case of curved black hole. So the rotation is coming from the geometry. It's not the rigid rotation of Newtonian universe. It's the space which is rotating, and that pulls everything along with it. Okay, and here we have helical paths for all the particles. These are the paths as seen from top of the z-axis rather. And so the lights, they have a helical path which is of the largest radius for all the particles, and particles moving slower than light, they also move along helices, but the radius of the helices is smaller, and the axis of the helices is along the rotation axis, the z-axis. Particles moving perpendicular to the plane of rotation, they move in circles, closed circles. They come back to the starting point. Whereas if the particle has a component of velocity along the z-axis, z-axis, it continues to move in that direction in a helical path. Okay, so Godel universe is not the only rotating solution in general relativity. There's this special von Stockham cylinder which was discovered earlier in 1936, but at that time it was not known that it had CTCs. This discovery was made much later in 1974 by Tipler. So the universe in which it was theoretically confirmed that there were CTCs, the first of those was the Godel universe. Then other interesting and useful rotating solution is the Kerr black hole. This is regarded as the end point of gravitational collapse. Then there are a large number of rotating dust solutions whose metric tensor is quite similar to the rotating Godel universe. Okay, so this is what Godel said was missing in his equations in the metric, the expansion. So this expansion was introduced and studied by a Russian physicist by the name Obukhov, and his modification of the Godel metric is also called Godel-Obukhov universe. Basically, it attaches a expansion factor to the spatial components of the metric. Interestingly, the angular velocity of the universe is high during the early stages of Big Bang. The universe is rotating faster, and as the universe expands, the rotation slows down and becomes very small at the scales, the time scales where we are now. Okay, so here we have the evidences for rotation. The evidences come from a number of sources. Basically, they have to do with polarization of the photons. You see the spins of the photons, it gets coupled with the rotation of the universe, and that generates certain planes of polarization. So in 1982, Birch claimed existence of a large scale anisotropy in radio wave polarization from extragalactic sources. He suggested this might be observational evidence for universal rotation and anisotropy. Then there were alignments of quasar optical polarizations, and the CMBR, cosmic microwave background radiation. This is a very popular the CMBR data. We expand the data in terms of what are called as spherical harmonics, monopoles, multipoles, dipoles, quadrupoles. So they found there was certain alignment in quadrupole and octopole, which was suggestive of a certain specific direction in the space. And this is the data set which has been used for predicting the existence of dark energy. This data set was created by a large team led by Perlmutter, and basically it consists of about 200 supernovas, quite distant but quite bright and a reliable source of redshift. So it provided direct evidence for dark energy and played a fundamental role in determination of cosmological parameters. So whether there was a certain sign of rotation that was analyzed for this data, but no clear signal was found for rotation or for ruling it out altogether. So we were not very clear about what this data set suggested. Okay, now this is what is called as Newton's bucket experiment. Let's say you have a bucket filled with water and you started rotating. So initially the bucket is rotating, the water is not rotating. But as the water gets dragged in the boundary layer, the water also starts rotating, but its surface assumes a parabolic shape. That comes from simple equations of centripetal force and pressure and height. So Mach asked this question: the bucket is rotating, water is rotating, and it's got this shape. Now he asked a question of relativity of rotation. He said, supposing the bucket is not rotating, but the universe is rotating around it, what's going to happen in that case? Will the water assume a parabolic shape in this case also, or no? So Mach argued that if the universe was rotating and bucket and water was stationary, the reaction of the universe, the inertia, would be such that the water should assume the parabolic shape which happens in the other case. But the Godel universe is anti-Machian. It says the rotation of the universe will not create such a situation that water assumes parabolic surface.
Because it's rotating slowly. According to one of your other slides, where the observable universe is an old universe, and this old universe, because of the expansion, rotates a lot slower, and at some slowness you can't observe the centripetal forces.
Yes, that's a point of view, that the amount of rotation is small, so the effect would be small. But from the equations which come out of the Godel universe, when we plug in the centripetal force and the inertial forces, so there again it is predicted that whatever be the rotation of universe, it will not affect the shape of the water surface. So that property is called anti-Machian. That Mach's concept of inertia and the relativity of the rotation, they work in a different manner in Godel universe. Now this was a surprising development. In this beginning of this century, people found that Godel universe has interesting properties when they are studied in string theory and supersymmetry. Number of papers on string theory, they refer to properties of the Godel background, and when the Godel background is used for studying of the strings, number of interesting properties they emerge, and number of extra supersymmetries also emerge due to the symmetries which are present in the Godel universe. Okay, and the embedding of the black holes. You see, black holes, they have a special metric. It is singular at a point, and let's say the expanding universe, that's also have a special metric. So can we have a metric which gives a smooth description of both of them? Can we have embedding of a black hole in the expanding universe? It turns out that we don't have a simple solution for that problem. We cannot straight away embed a black hole in an expanding universe. But in case of Godel universe, various black holes, they can be easily embedded. There is no problem with the embedding of the black holes in the Godel universe. Here Schwarzschild is the usual simplest black hole. Kerr is the rotating black hole, and Kerr-Newman is rotating black hole which is also carrying an electric charge. Okay, this is the last slide. This is the prediction which I am suggesting for verification of the rotation. It's called the anisotropic splitting of spectral lines due to coupling of photon spin with the spatial rotation in the redshifted 21 centimeter hydrogen line. Hydrogen is the main element of the universe. All the data of the redshift is coming from the redshift of this 21 centimeter hydrogen line. So the photons of this line, they get coupled to the rotation of the universe. So, but rotation is it's a special axis, special direction. So the amount of energy which comes from the coupling, that's going to vary with the direction from which the photon is coming. So there will be splitting of the spectral line, but it will have a anisotropic effect. It will be an anisotropic effect with the direction, the plus minus this second term, that's going to vary with angle with the axis of rotation. That's all. Thank you.
I have a question. So Klee talked about the superfluid, which by some property looks a little like this Gödel universe, the spiral, but the superfluid is a quantum mechanics theory. So do we have a quantum gravity version of the Gödel universe where you could have vortices?
Yes, as I
string theory maybe you told?
We do have Godel universe embedded in as a background in string theory and supersymmetry. People have analyzed various kind of fields in the Godel universe. For example, the neutrino field, the Dirac equations, and the spins of various type of particles, scalars, vectors. I believe that it should be possible to have a quantum gravity solution of the Godel universe in which the universe, the fluid as such, the matter distribution, the matter, whether it behaves like a superfluid, that's your question, right?
Yes.
The original Godel solution, the matter is pressureless dust. It has vorticity as such. So vorticity is there, but the various other properties of the superfluid, the motion and the frictionless motion, those properties have not yet been specifically inputted into the solution.
Do you believe it's an interesting work to do?
Yes, and Godel universe has been, this was actually a surprise that it has found interest in terms of string theory and supersymmetry.
So this is like a recent model, or it's not a recent model, right? Just like somehow recently people start get interested again.
Yeah.
Okay.
Till now, the interest was only in finding out the geodesics and closed time-like curves and finding the killing vectors. But then the emphasis shifted towards string theory and supersymmetry aspects and the black hole embeddings.
Do we have any data, the astronomy, data that support this kind of unique axis?
Yes. These two slides basically the data is going to come only from the photons and the spin of photons, how they get coupled to the rotation axis. So which leads to a polarization of the photons. So polarization of the radio waves from extragalactic sources, that does suggest that there is a evidence for universal rotation and anisotropy.
But didn't Paul Steinhardt said there is there is no evidence for anisotropy?
Yeah, so do you know who Paul Steinhardt is? He's, okay. So he told me that he doesn't see evidence for anisotropy in the universe.
That's right. A couple of those statements have come from the analysis of CMBR, cosmic microwave background radiation. That analysis showed that there's no anisotropy in the microwave background data. Cosmic microwave background data comes from that era of the universe when the photons decoupled from the matter, and so the radiation became free to traverse large distances. Till then the photons were interacting with the matter, but they became free to move, decoupled from the matter, and that is they are the photons of CMBR. But nevertheless, while generally it is claimed that CMBR data does not show any anisotropy, there is a certain alignment at the quadrupole and octopole level, which suggests that there could be anisotropy. It's not. There are certain evidences which say that yes, there is an anisotropy. Then there are other results which say that there's no anisotropy.
What is the evidence that says there's no anisotropy?
That evidence is based upon the CMBR data only.
Because you said the CMBR data shows special alignments along the quadrupoles and octopoles.
Yeah.
That indicates anisotropy.
Yeah. What happens is that the other higher multiple moments that disappears. Actually, what I should clarify, there is what is called as small scale anisotropy and the large scale anisotropy. The small scale anisotropy means you have this direction, you have this direction, something different happening, in between something else is happening. So this is small scale anisotropy. So CMBR data is not finding evidence for this small scale anisotropy, but for a large scale anisotropy, that point is not being ruled out. That is for the alignment of the quadrupole and octopole data.
So that's for isotropy,
Yeah.
not anisotropy.
Yeah. We have to distinguish between the large scale anisotropy and the small scale anisotropy.
And the data comes from the Planck, the Planck observatory, the new, or the WMAP? Because these data are very recent.
Yeah.
Yes, so they are still in.
But those data, the WMAP data, that's again for the small scale anisotropy, that at small distances nothing different is happening at small angular distances. But for a large scale anisotropy such as direction of rotation, that's a different set of equations and data.